We talked about trig in right angle triangles, which is great. But of course angles can be bigger than 90 degrees. So how do we deal with angles of any magnitude whatsoever? Here's the coordinate plane, and we'll chuck the unit circle on it, and I've just marked off the angles. So we normally start with 0 degrees out here of the positive x-axis, and we go around anti-clockwise. The quadrants also go anti-clockwise, so 1, 2, 3 and 4. Inside there I draw in what I call the butterfly. What it basically is 4 right angle triangles, because we know how to deal with right angle triangles, and there's the position we put them in, it forms that butterfly shape, and we use those to work out the angles of any magnitude. The acute angle we're going to work with always goes with the horizontal axis. So in each of those triangles, that's where theta would be positioned. In the first quadrant, everything's normal, of course, because it's between 0 and 90 degrees, and that's what we're used to dealing with. Second quadrant, also known as 180 theta, because have a look at where theta is positioned. So the angle we're dealing with, remember we start at 0 and go round, will be 180 minus the acute angle, that theta. So that's the second quadrant. Now how do we work out the sine, the cosine and the tan ratio? Well, we can read off the right angle triangle that we know about. But of course it's on a coordinate number plane. And so over here, the x values are actually negative. The y values are still positive. And when it comes to the hypotenuse, it's a distance, so it's always positive. So using that we can work out which signs are positive and negative. So sine opposite over hypotenuse would be a positive number over a positive number. Okay, sine's going to be positive. Cosine, however, is now adjacent negative. There'll be negative over a positive. The cosine will actually be a negative ratio, and similar with tan, it works out to be negative in that quadrant. We get to the next quadrant, quadrant 3, it's now going to be 180 degrees plus the acute angle. Sine now is negative, cosine is negative. It's the tan ratio that turns out to be positive. And then we get to our fourth quadrant, which would be 360 degrees, but take away the acute angle. And in that one, sine is negative, cosine's positive, and tan's negative. Now there's all sorts of ways people use to remember it. The old ASTC, all stations to settle, all sorts of things. So what do we use it for? If I have to find the sine of 260 degrees, and yes, of course you could use a calculator and get the answer. But how do we relate this back to the acute angle? Well, this is what we say. Well, 260 degrees, that's in the third quadrant. And we know sine is negative in the third quadrant. What would the equivalent acute angle be? Well, in the third quadrant, it's 180 plus the acute angle. So 180 plus 80 is 260, so it must be the same as sine 80. And if you do plug it in the calculator, you would see that you get the same answer as sine 260 when you just go negative sine 80. They do in fact give the same answer. So tan of 220, that's also in the third quadrant, but tan's positive, the acute angle would be 40 degrees. So it would be the same as tan 40. Sec, well sec's the reciprocal of cosine. 105 is in the second quadrant. Cosine was negative, so sec's going to be negative. It would be the same as negative sec 75. That works out to be minus 3.8637. 430, hang on a sec, that's bigger than 360. Well, it's a circle. So we can always subtract or add, depending on what we need to do, 360. So cos 430 would be the same as cos 70. A negative angle? Well, that just means I've gone clockwise instead of anti-clockwise. So if I go clockwise 67 degrees, so negative 67, that's the same as going anti-clockwise 293. Well, here's the interesting thing. Tan 293, fourth quadrant. Tan's negative, what's the size of the acute angle? 67. Tan is actually an odd function. See how it's got the function negative x is equal to the negative function x, minus 2.3559. Okay, here's a question. Find the coordinates then of P. It's sitting on this circle, radius 5, we know that angle is 30 degrees. Well, I could create that right angle triangle then. X over 5 would be cosine of 30, one of our exact ratios. So 5 times cos 30, 5 root 3 on 2. But the question asks for coordinates, so let's work out the y value as well. That one's 5 on 2, so there's our point. 5 root 3 on 2, 5 on 2. But what do we do with when it lands on the boundary? 0, 90, 180, 360. So these values. I create a fictitious triangle. This triangle is not actually a triangle. Here it is. The angle down there is 0. Well, by angle sum of a triangle, that means the other angle must be 90 degrees. Its length is 1, but the height must be 0, because if that angle is 0, in fact, I'm talking about a straight line. We could use Pythagoras. It ends up being 1. I can now read off this fictitious triangle. 0 degrees. Sine of 0 is 0. Cosine of 0 is 1. Tan of 0 is 0. 90 degrees, I can read those off as well. Tan 90, of course, is undefined, because 1 divided by 0, you can't do it. So it's undefined. 180 degrees. How do I work these ones out? Well, I still use the idea of which quadrant it's in. When it's on a boundary, then it doesn't really matter which quadrant I say I'm in. So let's assume I'm in the second quadrant. Sine 180 would be the same as the acute angle, which would be 0. So it's going to be the same as sine 0. That was 0. Cos of 180. Well, if I'm in the second quadrant, cosine would be negative, same as cos 0, negative 1. And tan also ends up being 0. 270, same sort of idea. Now, the reality is, now that we've got calculators, you can just punch them into the calculator and get the answer. If it comes up with an error, as it would with tan 90 or tan 270, you know it's undefined. Let's now draw the graphs themselves. Use the boundary values when you're plotting trig graphs. They're the important points to plot. So let's draw up an axis here. I'm going to draw the sine curve. I know it goes between 1 and -1, so I've plotted that on the y value. I'll now plot in all of those boundary values, so every 90 degrees. I might have got a bit carried away. I've gone all the way to 720 and back to -360 as well. Start with 0. Well, sine 0 was 0, so I plot that in. I know sine 90 is 1. But I also know is a nice regular pattern, so I'll plot all the other ones in. It'll go down, then up, and down, then up. And we draw a curve to go through all those. We're not playing dot to dot. We don't draw a nice zigzag. It's a curve, so we put a curve through all of it. There's y equals sine x. Now that we have the picture, we can answer some questions that we're used to asking. For instance, domain, or real x. There is no breaks there. Range, -1 to 1. Period. Trig functions have something called a period. And a period is simply how long until it repeats itself. Now, it has to repeat itself exactly. So you can pick any point you like. When's it back there? But just be careful. For instance, if you were to pick 0, well, it's back at 0 at 180, but it's not exactly the same, because at the origin the curve's going up, but at 180 the curve's going down. It's not until it gets to 360 it's going back up again. So it's got to be exactly the same. So you pick any point you like. Every 360 degrees it will repeat. I can look at this function and I can tell it's an odd function, rotational symmetry. Therefore, the sine of negative x will be equal to the minus sine of x, and that could be a useful fact that we'll come to use. Let's do cosine. It also goes between -1 and 1. Plot in those values. Now, cosine began at 1, and then it goes down to the axis. It also goes up and down, up and down, up and down. Draw that one in, and there's cosine x. They are in fact exactly the same graph. It's just we have a horizontal shift of how many degrees? 90 degrees. That makes sense. They're complementary ratios. Complementary add up to 90 degrees. So one curve is the other curve shifted 90 degrees. It therefore means if they're the same curve, they have the same domain, they have the same range, they have the same period. However, this one is not an odd function. If we look at this one, axis of symmetry, we have an even function for this one. That means the cosine of negative x will always equal the cosine of x. Well, let's look at tan. So again, plot in those boundary values. I haven't bothered with the y-axis. You'll see why when we draw it. What happened with the tan curve? We started at 0. Then we got undefined. So it's not in the domain. We draw in an asymptote. That pattern keeps repeating. So we got x-intercept, then asymptote, x-intercept, asymptote, x-intercept, asymptote, and so on and so on and so on. We know curves bend towards the asymptote. I know that in the first quadrant it's positive, so we're up here. Second quadrant negative. Third quadrant positive for tan. Then fourth quadrant. We get something like that. When you draw these, it is not a cubic. Do not draw a horizontal point of inflection like a cubic. It actually goes through at 45 degrees. Goes through at 45 degrees. And that gets repeated in each section. There's our tan curve. The domain, a little bit harder to write for this one. Yeah, it's all real x, except for all of these asymptotes. So what was a quick way of writing that? I said, well, I know the first asymptote was at 90, and then every 180 degrees there's another one. So I said plus 180k, where k is just some integer. Any multiple of that, we'll find another asymptote. Range is a little bit easier to write. It's just all real y. There are no breaks that way. Its period is only 180 degrees though. It only takes 180 to repeat. It has rotational symmetry, odd function. So the tan of negative x is equal to negative tan of x. I'm only going to do one of the reciprocal graphs, so let's do this one. I'm going to do cosec, which is the reciprocal of sine. But we've seen how we draw reciprocal graphs, so I'll apply it to the sine graph. Reciprocal graphs. X-intercepts became vertical asymptotes. So let's draw in all our vertical asymptotes. If I turn 1 upside down, it's still 1. All of those values of 1 and negative 1 stay the same. Where the original curve was below 1, the new curve will be above 1, and so on and so on. We're going to get a series of U-shapes because we've got to bend towards the asymptote. We end up with something like that. There's cosec x. Okay, so 6D and 6E.